Okay, let's go ahead and get started. Happy Friday. I hope everyone gets a chance to enjoy the unseasonably warm weather today. It's kind of wild that like this time last week it was like -5 or something, and now it's 60 degrees. So, yeah, Bean was like very excited on the way here. So I like street park my car, and he just like never knows which car is my car, but we were like walking here and he just stopped in front of a random car and was like, let's go somewhere, like let's do something. So it's funny. Okay, so today we're gonna talk about the order of a group. And we're also going to talk about subgroups. So we've now talked about groups for a couple of lectures, and we've seen some examples of groups. And we've seen examples where the groups had infinitely many elements, and also examples of groups with finitely many elements. And both of these types are very interesting, but specifically finite groups have like a lot of structure, and they're actually like an active area of research. So it's really, there's like a rich theory of finite groups, and we're going to spend a lot of time sort of like unpacking that and looking at what can happen. So we'll start off with just some terminology. So we'll define the number of elements of a group G is called the order of G. And note that this could be infinite. So if the group has infinitely many elements, you would just say the group has infinite order. So this is possibly infinite. And it's denoted as follows. So just a line and then G and then another line. Okay, so this is just like the size of a set. Just some examples. So a group with infinite order, just an example of that would be the integers. So this is infinite order. And then what groups of order 4 do you know? Can anyone think of an example? Yeah. So it would have 5. So it'll be like 0, 1, 2, 3, 4. Yeah. So one example is Z 4 with addition. So it'd have like the 4 elements 0, 1, 2, and 3. Can anyone think of another one? Yeah. Yeah, so U5. So this one has the elements 1, 2, 3, and 4 under multiplication. So that's another example. Yeah. You have N? 10. I think maybe, I forget. So 1, 3, 7, 9. Yeah, okay, so this is another example. Good, okay, so these are some examples of groups of order 4. And One thing to think about that we'll address in the future is like which of these groups are actually like the same as one another. So is there like a way to relabel the elements in such a way that I can really think of these two groups as acting in the same kind of way? So that's something that we'll like in the future we'll write down like a mathematically precise way to think about that. Okay, so that was about the order of a group. And let me just introduce a little bit of notation. Okay, so if G is an element of a group, then we'll write G to the n to mean multiplying G by itself n times. And this is an unambiguous thing to write because by the associative property, it doesn't really matter what order we do these multiplications in. And also, like, I'll caution that if your group uses addition, you may write n times G. But in general, when we're speaking abstractly about groups, we'll always think of multiplication as the operation, and we'll write it as G to the n. And then another two pieces of notation, so G to the 0 will just be the identity element of the group, and whenever I write G to the minus n, what I really mean is G inverse to the n. Okay, and last time we saw that elements of groups have unique inverses, so that allows us to just write G inverse is that's some element of the group, and then we can multiply it by itself n times. Okay, so then we saw the order of a group, and there's also going to be a notion of an order of an element of a group. So the order of some element G in a group G is the smallest positive integer n such that G to the n is equal to the identity. And if this doesn't exist, then you would just say that that group element has infinite order. So if this number does not exist, then we say that G has infinite order. And similar to how the order of a group was denoted, we would write this as like G with lines surrounding it. So that's how you would write the order of G. Okay, so I'm going to give you two problems just to warm you up to the idea of the order of an element. So the first one we'll deal with U of 15. So find the order of U15, and then also in this group find the order of the element 7. And then in Z mod 12 with addition, find the order of the element 3. So I'll give you some time to think about these two problems, and then we'll discuss Okay, if people converge to answers. So I got for this 8, and for the order of 7, 4, because you can just calculate 7 squared. So mod 15 is going to be 4, and then 7 cubed I got to be 6, and then 7 to the 4th is 1, which is the identity. So that's the smallest positive integer that gets you back to the identity. And then for the order of 3, again, just checking so in this group we're using addition. So 2 times 3 is 6, 3 times 3 is 9, and then 4 times 3 brings us back to 0. So the order of this would be 4. Okay, are there questions about those computations? Yeah. Did anyone get agreement or disagreement with this? 13? People got 13? Okay. Okay, so maybe this is 13, but then... Okay, then does this still come out to be... Okay, so I had an error. Okay. Other questions? Yeah. No. So the order of the group is just like the cardinality of the set that the group is on, yeah. Other questions? Okay, so for today, that was sort of all I had on the order of a group, but when we start talking about cyclic groups and things like that, there will be a lot of statements and nuance to the order of an element and the order of a group. But for now, let's talk about subgroups. So zooming out for a second and going back to like the general scheme of like what is math doing. So a lot of times when you introduce a new object of study, there's sort of a familiar pattern of things that you want to look at. And one of the first things that you look at is like objects of that type that sit inside of an object. So like, for example, in vector spaces, you looked at subspaces, and in like a topology class, you would look at topological spaces that sit inside of your topological space. So the idea of a sub object is like kind of pervasive in math, and it's always one of the first things that you look at when you introduce a new object. So what is a subgroup? So if a subset H of your group G is itself a group with the same operation as G, we say H is a subgroup. Of G. And sometimes this is written as like H less than or equal to G, but there's other notations that appear as well. So, so this is a subgroup, and two types of subgroups that you should be aware of, just like right off the gate, is the set containing the identity is always a subgroup. So this is a subgroup. And it's called the trivial subgroup. And then the group G is also a subgroup of itself. And if H is not equal to G, then you'd say that H is a proper subgroup. Okay, are there any questions about the definition? So we're going to see a lot of examples, and you may already be thinking a little bit about what some examples of subgroups that you might know, what some examples might be. But before we get into the examples, I'm going to give you a tool for testing if something is a subgroup. So this is a theorem. And the book really likes to give the theorems and statements catchy names, which I like because it makes them easier to remember. But the catchy name for this one is the one-step subgroup test. Okay, and it says the following, so we'll let G be a group. And H will be a non-empty subset of G. Okay, then if AB inverse is in H whenever A and B are in H, then we can conclude that H is a subgroup of G. Okay, so this definitely simplifies things because instead of needing to check that H satisfies each of the three group axioms, then instead you can just do this verification that if you have AB in H, then AB inverse is also in H. Okay, so let's prove this theorem. Okay, so to prove this, we're going to start off by assuming that H is a non-empty subset of G, and that it has this property. So we'll assume H is a subset of G, and H is non-empty. So this is, this symbol is just the empty set. So we're going to assume that H is non-empty and that for all A, B in H, we have AB inverse is in H. Okay, so then we have to prove that H is a group. So to do this, we're going to have to verify each of the three groups. Oh yeah, do you have a question? Oh yeah, okay, so that's A times B inverse, yeah. Yeah, other questions? Okay, so in order to prove that this is a group, we're going to have to verify the three group axioms, and then we'll also have to show that H is closed under the operation. So in other words, that for all A, B, and H, we actually do have that A times B is in H. Okay, so let's prove each of those things. So the first one is associativity. So why do we have associativity? Yeah, so the H just got its multiplication operation from the larger group G, and we know that that whatever the operation in G is, multiplication, is associative, and so that will also hold in H. So the operation on H is the same as in G. So, so we will have associativity. Okay, the next one is the identity. So how can we see that H contains the identity element? Yeah.
If we choose A and B to be the same, then A times A inverse is the identity, which we know is the same.
Yeah, so, okay, yeah, so let's take A to be some element of H, which we know exists because H was assumed to be non-empty. Then A times A inverse is in H, and A times A inverse is just equal to the identity element. So, so H does contain the identity. Yeah. So, okay, yeah, so the assumption that we made about H was that for any A and B in H, then AB inverse is in H, right? So I'm just taking A and A to be the two things. So then we know that A inverse is the, yeah. Okay, other questions? Okay, so the next thing is inverses. So we will have to show that H contains inverses. Does anyone see how to show that H has inverses? Yeah, so we have E and A are elements of H, which tells us by the assumption that E times A inverse is in H. And of course, E times A inverse is equal to A inverse. So we know that inverses of elements are in H. Okay, so now the last thing we need to show is that H is closed under the operation. So specifically, like when I say that H is closed under the operation, what I mean by that is that for all A and B in H, then also A times B is in H, right? So if we have a group, we want to be able to multiply any pair of elements and get something else in the group back. So we do need to show that H is closed under the operation. But now this is pretty easy because we've already shown that inverses are in here. So if we let A and B be elements of H, then by what we've already shown, we know that B inverse is in H. So then just applying our assumption to A and B inverse, this gives me that A times B inverse is in H. And of course okay, well maybe not of course, I'll explain this for a moment. So B inverse will just be, this will be AB. So, okay, so why is B inverse inverse equal to B. So we showed that inverses in groups were unique, and we already know that B is the inverse of B inverse, right? Okay, so we know, let me maybe say a few words about this. So we know that B times B inverse is equal to the identity, which means that B is the inverse of this thing. So if I apply a -1 to that, then that has to just give me back B. Okay, so that completes the proof. Oop. Are there questions about anything in the proof? Yeah. Okay, yeah. So yeah, why? So we showed that the identity element of the larger group G was in H, right? And we know that for any element of G, E times G is equal to G. And so that will also hold true when we just restrict to a subset, yeah. But yeah, that's good to point out that part of what the identity axiom is saying is that the identity behaves in the way that you think that it does. Yeah. Other questions? Okay, so let's maybe see some examples. So how we use this test typically. So usually you'll have some description of what your subgroup is supposed to be, and you first need to show that it's non-empty. Do you have a question?
Yeah, sorry, I was just wondering if every subgroup satisfy this test, or is this just only identified as a subgroup?
Yeah, so if you do have a subgroup, it has inverses, right? So if I have any A and B in the subgroup, then I can take B inverse, and then I can also multiply those two things, and they still have to be in the subgroup. Yeah, so this really is, this is an if and only if. Okay, so typically how this is used, you need to show that the subset is non-empty, and typically the identity element is the easiest one to show that it's in there. So typically to show H is non-empty, you'll want to just start by showing that the identity is in H, and then just assume A and B are elements of H, and then prove that AB inverse is an element of H. Okay, so let's see an example. So I'm going to let G be an abelian group, so I can commute the elements. And I'll let H be the elements with order at most 2. So just to write this down as a set, H would be the x's in G such that x squared is equal to the identity. And then let's prove that H is a subgroup. Okay, so the first thing that I need to show is that H is non-empty. So why is H non-empty? Yeah. Yeah, so E squared is equal to E, so that means that E is an element of H. Okay, so H is not empty. Okay, and then step two, step two of the one-step subgroup test. So step two, we're going to suppose A and B are in H, and then we want to show that AB inverse is also in H. So let's just do a little calculation and see what AB. So, right, okay, so we want to take a look at this element AB inverse and see if it satisfies this criterion. So we'll take AB inverse and square it. Okay, so we get, so that's just multiplying this thing twice. Blah. So we get AB inverse, AB inverse. Okay, and then now, since I assumed that my group was abelian, I can commute these elements. So I'll have A times A, and then B inverse times B inverse. So this is, here I've used the fact that the group is abelian. And then this gives me A squared times B inverse squared. Okay, so then what should I do from here? Yeah. Yeah, okay, so we know that A squared is, so A is an element of the group H, the sub, or the thing that we're trying to prove is a subgroup, so this becomes E, and then B inverse squared I claim is equal to B squared inverse. So again, this is sort of like a uniqueness of identity thing. So if I had, so if I want to know what is B squared inverse, so this would be the thing that brings B squared back to the identity. So if I want to cancel out both of my B squareds, then I need B inverse, blah. But I think I have this backwards. B times B. Okay, so this gives me E times E, which is E. So that in total shows that AB inverse squared is equal to E. So AB inverse is an element of H. So then by the one-step subgroup test, we have that H is a subgroup of G. Okay, so now as an exercise, I'm going to ask you, yeah. Does a group have to contain what? Yeah, yeah. Okay, so for that exercise, I want you to find all subgroups of Z mod 6 with addition. Okay, so I'll give you a few minutes to think about that, and then we will discuss. Okay, so what subgroups of Z mod 6 do we have? Yeah. Yeah, okay, so one subgroup is 0, comma 3. So this is a subgroup of order 2. What other subgroups do we have? Yeah. Yes, there's also 0, 2, 4. This one has order 3. Any other subgroups? Yeah. Yeah. So all of Z6, and then also just the one containing the identity. So this one has order 6, and this one has order 1. Are there any others? You have one? So 0, 1, 5. But this doesn't contain like 1 plus 1. So yeah, so this one's not a subgroup because it does not contain one plus one. Okay, so does anyone hey, did anyone notice anything or like have any conjectures just based on this one example? Yeah.
So like the first one is every multiple of 3, and the second subgroup is every multiple of 2. So maybe the subgroups of Tn are like the multiples of the factors.
Yeah, okay, so like what is a different way to describe this group? So this is like the set of n times 3 for integers n. And then of course like mod 6. And then this one is all the multiples of 2. So yeah, of course, like, okay, so if you have a subgroup, then all of the multiples of any element of that subgroup definitely need to be in there, right? So that is like potentially one way of generating subgroups is by taking a single element of your group and just looking at multiples of that. So we may wonder so in general, is the set g to the n such that n is an integer? So now I'm using the multiplicative notation, but is this a subgroup? Good, and then in general, like, is this all of the subgroups? So we'll see that in general, the answer to this question is no, but in certain scenarios, this is true. Okay, good. Any other observations from this example? So another observation that you might make is that the orders of these subgroups divide the order of the whole group. So that is something that turns out to be true in general, that the orders of subgroups, and we'll prove this later, but the order of a subgroup always divides the order of a group. Are there any other observations? Okay, that's it. So one thing you may think about is like what group does this act like? So I would relabel this as Z2 because we can really just think of this as this is the group operation is behaving in the same way as addition mod 2 with the elements 0 and 1. And similarly, we could sort of rethink of this one as Z3. So that's something else to think about. Okay, so I will see you all on Monday, and I hope you have a good weekend. And on Monday, we're going to do some more subgroup tests. And looking into next week, we're going to be looking at something called cyclic groups. So we want to show that b squared inverse is equal to b inverse squared. So what I need to do is like find what do I multiply b squared by in order to get the identity. So b squared times something is equal to the identity. Well, this is like clearly b inverse b inverse.
I can see why that something is b squared. Because if we think of like b squared as like one just element,
Yeah.
then I can see why that something is b squared is just why is that b inverse b?
So then this is why is okay, yeah, because if we just like did this computation like b inverse b inverse, like that multiplies
Okay.
the identity.
Yeah, okay. Oh, okay, and so that's why, so b inverse, so this is definitely this. But from this we can say that, oh,
Yeah,
okay,
yeah,
I see.
yeah.
Thank you.